This is my presentation on the topic Loop the Loop. Imagine you are trying to create a procedural texture to generate terrain in your game. I will use Wally Noise as an example. First, you have a texture of 512 by 512 pixels. In the texture, you generate a number of points, each at a random position inside the texture. Now, you need to get a value for each pixel inside the texture. Here, we start at a pixel of 0 on the x-axis and 0 on the y-axis. On this pixel, you loop through the list of points that you generated and find the point that is closest to this pixel. Then, the distance between the closest point and this pixel will be the pixel's value. Here is how it will look like in pseudocode. In the outer for loop, you go through each pixel on the x-axis. Then, the next for loop will go through each pixel on the y-axis for this specific x-axis. Then, in the next for loop, it will go through each point that is generated and find the closest distance value between this pixel, x, y, and the points generated. The resulting noise will look something like this. Now we hop on to Unity to try generating this and see what happens. Here, I have around the same settings as the example I gave earlier, and once I click generate, it will generate the map and also give me the time it took to generate it. As you can see here, it took 0.205 seconds to generate, which is not that bad, right? Now, what if you want to animate this and update it every frame? Now, let me turn on the frame per second indicator so we can see how many frames we're getting. Now when I press loop, it will go through the animation and we can see how many frames we're getting per second. As you can see, the noise map is currently animating and it's not running very smoothly. We are only getting a measly 5 frames per second. Now, here's the problem. Computation time of 0.185 seconds is too high to generate noise in real time at a playable frame rate of 30 frames per second. Do we have a way to pinpoint where exactly the bottleneck is happening? Well, yes we do. Introducing the Unity Profiler. With the Profiler, as we run our program, we can see the performance metrics of all the things that are happening in each frame. Now, when I start the animation of the texture, you can see a huge spike on the graph. We can scroll to that frame to see where the bottleneck is happening, in which it is indicating here on this PGGE test script in the update method. We can go a step further and turn on Deep Profile, which will give us a more in-depth analysis on the location of the bottleneck. With Deep Profile turned on, we can see that the bottleneck is happening at wallynoise.generateNoiseMap. There seems to be over 3 million calls for the vector2.distance function and the mathf.min function. And in total, all these functions added up together adds up to 1828 milliseconds for computation time. Let's analyze what we had and see where the root of the problem is. First off, what is the time complexity of this nested for loop? We have 3 layers of for loop, which will give a time complexity of O(n cubed), which is not very optimal. Next, we can find out how many calculations are being done in a single frame. We have 512 pixels in the x-axis, and for each of the pixels in the x-axis, we have 512 pixels in the y-axis. Next, we have 12 random points which we generated, so that's 512 multiplied by 512 multiplied by 12, which brings us to 3 million distance calculations in a single frame. What's worse is this scales exponentially. 1 more points, 50 points will give you 13 million calculations. 100 points will give you 26 million calculations. Or you want your texture to be in a higher resolution. 1024 by 1024 will give you 12 million calculations, and 2048 by 2048 will give you 50 million. This is just not sustainable at all. Now that we have found and analyzed the bottleneck, how do we improve the performance for this function? We have a myriad of ways to solve this problem of nested for loops. First, we will explore the Unity job system. Normally, our code will run in a single thread, so our pixels are going to be processed sequentially, one by one from pixel at 00 to pixel at 511511. But with the Unity job system, we are able to utilize the power of parallel processing to place the pixels into groups, and let multiple threads handle the different groups' calculation. This helps us cut down on the computation time needed for the processing of the pixels. Here in our code, I had modified our initial noise generator to utilize the Unity job system. This is the before, and this is the after. The iJob parallel for interface is a type of parallelized job in the job system to process elements of an array concurrently, especially where the same operations are made for each element in the array. There are other interfaces in the job system which have their own users and function for multi-threading capabilities. Here, we can see the result of our implementation. The time taken for unoptimized code takes 0.185 seconds. Now, with the job system, our generator only takes 0.044 seconds. This is a whopping increase of around 78%. We can further improve this timing a little by utilizing the burst compiler that Unity provides. The burst compiler is designed to work alongside Unity's job system and helps improve performance by generating highly optimized machine code that the machine can interpret more efficiently. With this small tag burst compile here, our timing for the generator drops to 0.19 seconds. An alternative way to utilize parallel computing is to utilize our graphics processing unit, also known as GPU. Our GPU is well suited for parallel computing due to the way it is designed. It has a huge number of cores which allows it to perform many calculations simultaneously, making it highly effective for tasks that can be parallelized. The GPU also highly specializes at single instruction, multiple data operation like the one we have for our noise generator. To tap into the GPU's potential, we can explore GPU-friendly APIs and features. In Unity, we can use compute shaders to help offload computations to the GPU. So here in Unity, I have roughly integrated the noise generator into the compute shader. I can change and update the parameters in real time with decent performance. I can even increase the amount of points and even add additional layers of noise on top without hurting the performance that much. As you can see, this is a very powerful way to mitigate performance bottleneck from nested for loops, but it comes with its own drawbacks. Passing data between the CPU and GPU is a very expensive operation and can sometimes result in worse performance than anticipated. There are many other ways to optimize performance for nested for loops. Coroutines, for example, can be used to spread out the execution of the code over several frames instead of a single frame. It can also help with further parallelization with Unity's job system. Another way is to have better data structures. With better data structures, you can have optimized search operations to find the data you are trying to process, even if your dataset is large. It can also help reduce the time complexity of your code, which would result in better performance. In conclusion, nested for loops are essential in the development of games, but they can cause a serious headache performance-wise. With the Unity profiler, figuring out bottlenecks will be a piece of cake, and the different ways of resolving the issues, like Unity job system or GPU parallel computing, will easily curb these performance challenges. With the right tools and techniques, we can harness the power of loops without compromising performance. Thank you for listening to my presentation.